Welcome to this video demonstration of the process of creating the schematic symbols for a 512 meg by 16 DDR3 DRAM part using the CadEnhance Part Builder EDA productivity tool. There are four main steps to building a part in Part Builder. The first is to provide the pin data for the part in the most accurate format available. The second is to create and edit the symbol description language, SDL file, to describe how we want the symbols built. The third is to set up the properties we want to attach to the part and the values of those properties. And the last is to let Part Builder generate the part files for the selected EDA tools. After the initial steps are completed, we will view the parts with a critical eye and tweak the SDL to get the symbols to look just the way we want. The first step in building any part with Part Builder is to figure out what pin report type will work best for that part. Most DRAM manufacturers will provide an IBIS model for their DRAM devices for signal integrity simulations. Part Builder can extract pin names, pin numbers, and pin types from an IBIS file, so the best option is to download the IBIS model for the DRAM component and extract the pin data from there. If there is no IBIS model, we can download the datasheet and cut and paste the information into one of several formats. We can also use the free NitroCloud PDF converter to convert the datasheet to Excel tables for easier cutting, pasting, and reformatting. Micron does provide an IBIS file for this part, so this will prove to be the quickest and most accurate way for Part Builder to extract pin data for the part. We download the IBIS model file from Micron. It comes in zip file format, so we need to extract the actual IBIS model file from the zip archive. We unzip the folder and take a look at the contents. The folder contains the v91a1.35.ibis file. If we take a look at that file, we can see a header at the top that says it's an IBIS 4.2 model. Looking at the file header again, we can see that it contains information for 6 Micron parts in the model. So we will need to choose which component package we want to use for the pin data. When Part Builder reads this file, it will pop up a window prompting the user to choose one of the 6 component/package instances it finds. In the header, we can see there is a component called MT41K512M16HA. And if we peruse down to line 478, we can see the package model V91A 96 ball _ PKG. That is the part we will be building. We start Part Builder. It prompts us to select an existing part, create a new part, or copy a part from an existing folder to a new folder. The recommended practice for Part Builder is to create a folder for each part you want to build. We choose New Part. We pick the C:CadEnhance workdir/myparts directory and name the part DDR3 _ DRAM _ IBIS _ demo. We click the Create New button, and Part Builder will prompt us to save the new config file, and then we will click the Done button. Now we configure Part Builder to use the IBIS model. We use the pin report type pull-down entry and browse to select the IBIS file type. Then we click the Browse button next to the pin report file entry to find the v91a1p35 IBIS file. Part Builder will prompt us to copy that file to our new local working directory, and we choose Yes. We also set the num pins field to 96 since we expect 96 pins. And next, we use the Config Save Configuration menu to save our first changes. Once the initial configuration selections have been made, we double-click the Read Pin Report operation on the main GUI. Part Builder will read the selected IBIS file and find the 6 component package pairs we previously discussed. It will then pop up a window prompting us to choose the desired component package combination. We select the MT41K512M16HA V91A 96 ball package combination. Now Part Builder will use its knowledge of the IBIS format to find the pin name, pin number, and pin type for every pin in our selected component. It will also notify us that it found 96 pins in the selected pin report file down in the status window. We can open the Pin Explorer window to see the pin data that was extracted from the IBIS model. We can see the pin names, pin numbers, and pin types. Notice at this point in the flow, the assigned symbol column will be unassigned, and the side and modifier columns will be empty, since we have not created the SDL to map the pins to symbols yet. If we look through the pin list, we can see the pin names that were extracted and also verify them against the pinout shown in the PDF datasheet. A quick check shows us that DQ13 is found at A2, UDQS is found at C7, UDM is found at D3, and if we scroll to the bottom we can see reset is at pin T2 and VSS12 is found at pin T9. All the power pins have a suffix automatically added to them to make the pin names unique. We can use the select match filters to filter the list to find pins that match certain criteria. Here we type CQ, DQS in the pin name field to find all pins matching CK and DQS, and notice that some of them have the pound character. At this point, we have a choice whether we want to rename any of the pins extracted from the IBIS model. We wouldn't want to do this in the IBIS file itself, since any edits we make could affect the integrity of the file. We also might need to update the file from the vendor sometime in the future, and then we'd have to go back in and make those changes again. Instead, we will use the pin renaming feature provided by Part Builder. Here we will use the rename function to change the DQS and DQS pound pin names to DQS_P and DQS_N, and the CK and CK pound to CK_P and CK_N. This will let the downstream EDA tools have an easier time identifying them as diff pairs. We open the More Options window to enter the rename rules required to clean up our pin names the way we discussed, and we use the rename rules entry to type in the rules in the required format. There is more information about specifying rename rules in the online documentation provided at docs.cadenhance.com. We close the More Config Options window and get prompted to save the new settings. We say yes. Now we will run the read report step again with a new setting, and Part Builder will rename those signals. We open the Pin Explorer window and scroll through the pin list where we can see that the pins we wanted to rename have an extra entry in the Orig Name column, and we can use that to verify that the rules we wrote were followed. Running the Read Pin Report step also enabled the SmartFrac feature, which automatically generates symbol description language file templates for us. The SDL template files contain all the signal matches and power pin matches which we need to describe every pin in the part. The matches are compressed down to the minimum necessary to save time and required effort. For example, with this 96-pin DRAM part, SmartFrac creates the 17 signal match statements and 8 power match statements needed to describe our symbols. Now we use the auto-generated template to create the symbol description file. We have a choice to use a plain text editor or a spreadsheet tool to edit the SDL file. In this demo, we will use Microsoft Excel. We choose the Config Explore Current Part folder selection to open a File Explorer in the current directory. We open the AutoSDL-template.csv file, resize the column so it's more readable, and then save it as symbolorder.xlsx. The auto-generated SDL starts with a large section of comments providing information and hints on how to create SDL. Any row starting with a hashtag is ignored when Part Builder reads the file. Row 27 starts the real SDL statements created by SmartFrac. The signal symbol placeholder equals directive starts the first symbol, which ends at the semicolon at row 45. The SDL elements are laid out in columns in the spreadsheet. The symbol name directives are in column A. The pin location modifiers are in column B. Any extra modifiers are included in column C, and in this case we can see the D pair modifier for CKP, LDQS, and UDQS, since SmartFrac identified those pins as diff pairs. Column D is the double arrow separator between the modifiers and the pin match. Column E is the actual pin match, and column F is a comment SmartFrac used to tell how many pins it found for that match. The job now is to edit the spreadsheet using the row cut and copy operations to order the pins the way we want them to be placed on the symbol. We will also choose the size for the pins that currently have the choose side location modifier. We will use row insertion to add spacers to make the symbol more functional. At first, we will describe the part as two symbols, the first containing the address, control, and data pins, and the second one containing the power pins. So the first thing we will do is change the name of the symbol placeholders created by SmartFrac. We rename the first symbol placeholder DRAM mem pins. This will be the name that shows up on the symbol. and the second symbol DRAM power pins. We will group the DQ7-0 LDQS and LDM pins together, and the DQ15-0 and UDQS and UDM pins together. We will change the choose side to the right side for the DQ and DQS in-out pins. Note that the DQS pins are prefixed with a D pair modifier, so we only need place the _P pin, and the _N will automatically be added below it. Next, we will reorganize the address and control pins on the left-hand side and place some spacers between the bigger buses and clocks. We will add a BSS+2 command to start a new section in the current symbol between the address and data pins, and we will move the VREF_CA up from the power section to the address section, and the VREF-DQ to the DQS section. Now we organize the power pins. We put VDDQ at the top and change it to the left side. We put VSSQ on the right side underneath it, and add a bang BSS+3 to start a new section. Then we move VDD on the left and BSS on the right, add another BSS3 to start another new section, where we place the NC pins on the right and ZQ on the left. We use BSS+3 to add 3 spacers between the sections, but we might want BSS+4 or 5 to create even more space for the decoupling caps we will have to place in the schematic. The CadEnhance tool distribution includes a utils directory where an Excel macro resides, which lets us quickly save an Excel worksheet as a .csv file, named after the tab name at the sheet at the bottom. You will find this very handy and should check out our other videos to see how to set it up. We rename the tab symbol order and use the macro to save a copy of the data as symbolorder.csv. Now that we've created our first cut at the SDL file, we select Browse for the symbol description file and choose the symbolorder.csv file we just created. Then we double-click the Build Symbols operation. As long as our SDL file finds a place for every pin, this operation should run successfully, and it will produce a set of symbols for each enabled EDA tool, which we can view with the Part Builder Symbol Viewer function. Let's take a look at the symbols we created. The Symbol Viewer currently supports Allegro HDL and Mentor Viewer function, but the OrCAD symbol will look just like the Allegro HDL symbol. We will notice that the address pin ordering looks a little off, since it goes from A7 down to A0 and then A15 down to A8. We could also use a space between the BA0 and the RAS pin, and a space between Reset and VREF-CA. We would also want to move the UDM signal down to the start of the DQ15-0 bus, and maybe move the VREF-DQ a spacer or two away from the UDM. The DQS strobes on the right should also be separated a bit from their DQS buses. Here we use the power of SDL. We can fix all of these issues with just a few controlled edits. We fix the address by moving the A15 to 8 pin match above the A7 to 0 pin match. We copy a left spacer between the BA2 to 0 pin match and the RAS pin match. Then we copy another left spacer between the Reset and VREF-CA pin matches. We add a BSS+2 after the LDQSP diff pair to start a new section for the next data bus, so UDM will automatically move to the start of the DQ15 to match the start of the DQ15 to 0 bus. And we add 2 right equal spacers between DQ0 and LDQS, and DQ8 and UDQS. Then we save our changes to the symbolorder.csv file. Now we rerun the build symbols operation to regenerate the symbols and take another look. We can see that we fixed what we wanted. The address bus is in order, there is good spacing between the control signals, and the DQ pins are aligned well with their strobes and DM signals. We can also look at the power pin symbol and see that it looks pretty functional. Going back to the address data pins sections, it seems that it would make sense to split the address and data into their own symbols, since the functions look somewhat separate. This is easy with SDL. We just end the first symbol by inserting a new row on top of row 45 and add a semicolon to end the first symbol. Then we change the first column of row 46 to be DRAM_DQ pins equals, which starts a second symbol. We go back up to row 27 to rename the symbol DRAM A control pins, and then save the symbol order.csv. We rerun the build symbols operation one more time. When we look again, we see we now have three very functional symbols to represent this DRAM device. The first named DRAM A control pins with just the address and control pins. The next named DRAM DQ pins with nicely grouped data masks and strobes. And the third, DRAM power pins. This concludes the demonstration of the CadEnhance Part Builder tool using the IBIS pin report type flow. To try this demo out yourself, go to www.cadenhance.com/free-tool-downloads. Select the latest version to download and follow the directions to request a free 30-day demo license. At your request, CadEnhance will provide you with all the data files required to build this part. Thank you for watching.